morning all of you. Now I am going to discuss about spectrum analysis. So what is this meaning of spectrum analysis? So the study of energy distortion across the frequency spectrum for a given frequency is called spectrum analysis. So for any wave, for any wave, whatever the energy distortion happening, for studying this study of this energy distortion is nothing but the spectral analysis. So the instruments which show this analysis graphically, so is known as spectrum analysis. Usually the instrument used is CRT. So an instrument which graphically represents the energy distortion of a signal as a function of frequency on cathode ray tube is called spectrum analysis. Generally, for a cathode CRO, cathode ray oscilloscope, we will be having a time domain. Time domain will be considering. But in the spectrum analyzers, we will be using the frequency domain. So, so this spectrum analyzer is using this frequency domain. So in spectrum, the use of this spectrum analysis is you can study about the bandwidth, frequency stability, harmonic distortion, difference in type of modulation. So all these information we can get from the spectrum analyzer. And during the spectrum analysis, we will divide the frequencies into two range of frequencies. The frequencies which are less than 10 megahertz, frequencies which are less than 10 megahertz are called audio frequencies, and the frequencies which range from 10 megahertz to 40 gigahertz are known as radio frequencies. So these are the two major categories of frequencies, and the characteristics of special and spectral analyzers are the frequency resolution, dynamic range, sensitivity, sweep desensitization. So these are the characteristics of spectrum analyzers. Coming to basic spectrum analyzer, this is the block diagram of the basic spectrum analyzer. In this basic spectrum analyzer, for which frequency input we need to analyze the spectrum, that is given to the input attenuator. So what does this attenuator does? This attenuator will attenuate the unwanted frequencies. It will allow only the required frequencies and stop all the other frequencies, and it will provide the frequencies for which you want to study the information. So that frequencies are provided to low pass filter. So this low pass filter will take off the any harmonics present, and it will allow those low frequency band range frequencies to the output. So it is given to the mixer. So mixer means it is nothing but the taking the difference of two frequencies is nothing but a mixer. So here from the LPF we are getting one frequency, and from the voltage tuned oscillator. This voltage tuned oscillator will provide another frequency. So the difference of these two frequencies are given output from the mixer. From the mixer you will be getting the output, difference of the two frequencies. That output is called the intermediate frequency, IF, intermediate frequency. If that intermediate frequency is of less magnitude, is weak, then this IF amplifier will amplify that weak signals, will strengthen that weak signals, and it is given to the detector. So this detector, what does it does is it will detect the frequency range, and it will show the detected frequencies onto the CRO. It is given to the Y plates of the vertical deflection plates of the CRO. So and for X plates of the CRO, from the sweep generator, a sawtooth waveform is given. A sawtooth waveform is provided to the X plates of the CRO. Why only sawtooth waveform is given here? Because if we give sawtooth waveform to the X plates, then only you will be getting the whatever wave you are giving to the Y plates, that will be projected on the CRO screen. So that is why you will be providing with the sawtooth waveform to the X plates, and for the Y plates, whatever waveform you need to measure, that is given to the Y plates. And the other thing is it is grounded here. Okay, this is the block diagram of the basic spectrum analyzer. Coming to the spectral displays, this, what is the difference between the cathode ray display and spectral displays? So the CRO will be showing the time domain, whereas in the spectral analyzers it will be showing the frequency domain. And the spectra which you need to study in the spectral displays are, first one is continuous wave. If you provide a continuous wave to the spectrum analyzer, then you will be shown only a single spike will be obtained on the screen. Whereas for the if you are giving with the amplitude modulation, then you will be noting three spikes. One is the middle one, that is FC, carrier frequency. On the other both sides of the carrier frequency, you can observe two side bands. So this is for the amplitude modulated signal. Under the phase modulation, you can see infinite number of sidebands here. You can see infinite number of sidebands in the phase modulation. During pulse modulations, you can observe the sums and difference of the carrier and all the harmonic components contained in the pulse are produced. So this is how the spectrum will look like for different signals. So for a continuous wave, then the spectrum will be a single spike, and for amplitude modulation, a carrier frequency with two side bands will be observed. For phase modulation, infinite number of side bands will be observed, and for pulse modulation, the sums and differences of the carrier and all harmonic components contained in the pulse are produced. So this is about the spectrum displays. Coming to the next topic, it is vector impedance meter. So the name itself, this meter is used to measure the impedance. Then why this vector name is given here? So because impedance means it is the sum of vector sum of resistance plus reactance. Resistance plus reactance, that is R plus Jx. Z is equal to R plus Jx. So that means it is nothing but a vector. If you represent in the rectangular form, it is represented as R plus Jx. If you represent it in the polar form, you can denote it as Z at an angle phi. Z at an angle phi. Z indicates the magnitude and phi indicates the phase angle. So our aim is to measure the magnitude, impedance magnitude, as well as the phase angle. So this how these two are going to be determined. Now let us see. This is the vector diagram of the this is the block diagram of the vector impedance meter. So initially a constant current source is taken. So here this constant current source will be providing a constant current. That constant current is given to the unknown impedance. Let us suppose you need to measure this impedance Zx. So this Zx can be written as magnitude Zx at an angle phi. So this magnitude is represented here in the magnitude meter, and phi is represented in the phase meter. So this is the unknown impedance which you are going to be measured. So that current is allowed to pass through the unknown impedance Zx. So whenever the current is passed through the impedance, then what you are going to get a current, that is a current multiplied with the impedance, so that voltage can be produced. But here this is the current only, it is getting the current. So that means current multiplied with an impedance, you will be getting the voltage. So this is nothing but the voltage, and this current to voltage converter is taken, so that this current to voltage converter will have the phase angle of the current flowing through the impedance. So that means this is the current. This is the current angle. So impedance means Z at an angle phi, right? So phi indicates the angle between the voltage and current. So you need to measure the angle between voltage and current. You need to measure. So that means if you consider here, this is I, this is the current, current, current you are going to get, and from here another current which is nothing but the passed through the impedance. So from this you can get a voltage signal. So this is one phase angle and this is the other. This is one voltage and this is the other voltage. Between these two voltages, whatever the phase angle will be there, that will be represented by the phase meter. So here I to V converter, it will convert it to the current to voltage. So this is, if this is voltage is of less amplitude, then this can be amplified by using the AC amplifier. Then you will get a voltage here. So the angle between these two voltages is led by the phase meter, that is the phase angle. And for determination of magnitude, this voltage is given to the precision rectifier. From the precision rectifier, it is connected to the Z magnitude meter, so that impedance can be measured here. So if this is the impedance and this is the phase angle. So Z at an angle phi indicates the impedance. You can measure the impedance by using this vector impedance meter. Next one is Q meter. Q indicates the quality factor. So quality factor, you will be measuring the quality factor by using the Q meter. So this instrument, so the instrument which is going to measure the quality factor is nothing but the Q meter. So what is the formula for quality factor? So quality factor is equal to omega L by R, that we all know that. Q is equal to omega L by R. That is, it is the ratio of reactance to the resistance. Or we can also mention it as it is the reactance voltage, that is inductance voltage to the resistance voltage. We can also write that. So from that you can explain the working principle. So the Q meter measures the quality factor of the circuit, which shows the energy dissipated by it. So omega L means energy stored and R means energy dissipated. So the ratio of energy. So this Q meter measures the quality factor of the circuit, which shows the total energy dissipation. So omega L represents the energy storage and resistance represents the energy dissipation. So the ratio of these two will give you the quality factor. So it also explains the properties of the coil and capacitor. The Q meter used in the laboratory for testing the radio frequency of the coils. And this is the block diagram of the Q meter. So initially we are using an oscillator. This oscillator will generate some amount of voltage with one frequency. So that is passed through a resistor RSH. This RSH value will be taken as low as possible. That is, it is equal to 0.02 ohms. So that resistance is connected in this circuit. So whenever it is connected in this circuit, then in parallel to this resistance, there is a thermocouple voltmeter will be provided. This thermocouple voltmeter will show the voltage which is across the resistance RSH. So that voltage is now acts as a source to the circuit. This voltage will act as a source to the circuit, and this is connected to the coil. So this coil will have a resistance R, inductance L, and this is connected to a capacitance here. This is the tuning capacitor. So this tuning capacitor you can vary the capacitor such that the circuit will be under resonance. So that R, L, C, all these three are connected in series. So that whenever a series resonant circuit will be formed here. So whenever the circuit is resonate, when it resonates, then it indicates the EC indicates the voltage across the capacitor, which is having the quality factor. So this EC is nothing but the capacitor voltage, and the ratio of this capacitor voltage to the input voltage, that is EC by E indicates the quality factor. So this EC is equal to Q into E is the quality factor. So likewise